Welcome to the lecture 4 of the atmospheric dynamics. Let's discuss the structure of the atmosphere, static atmosphere. Under that, we will discuss the hydrostatic equation. So, the content of this presentation is taken from An Introduction to Dynamic Meteorology, 5th edition, by James R. Holton and Gregory J. Hackett. Let's discuss the hydrostatic equation. Let us imagine we have a column with unit cross-sectional area and we have a block of air inside it. So in the absence of atmospheric motion, so the gravity force must be exactly balanced by the vertical component of the pressure gradient force. So the downward force exerted by gravity on air is given by rho g dz, where rho is the density of air, g is acceleration due to gravity, and dz is this thickness. So the net pressure force given by the difference between the pressure, the upward force across the lower surface, and the downward force across the upper surface. So which are represented here P and P plus Tp. So the net pressure force is given as minus Tp. So the symbol minus represents the pressure decreases with height. So that's why it is taken minus dP, the net pressure force. So according to that, so dP by dz is equal to minus rho g. So how we get it? If you equate it to rho g dz equal to minus dP, you can write it as dP by dz is equal to minus rho g. So this equation number 1 is called the condition for the hydrostatic balance. So now, by integrating that equation 1, which is dou p by dou z is equal to minus rho g, from a height z to the top of the atmosphere, we find that, so we can write P of z is equal to integral z to infinity rho g dz. So again I can show you that equation. So dP by dz is equal to minus rho g. This dz is taken to the right hand side and then we will integrate that. So from z to infinite. So we will obtain P of z is equal to integral z to infinity rho g dz. So from this expression we can understand that the pressure at any point is just equal to weight of that unity cross section column of air. So this hydrostatic equation can also be expressed in terms of geopotential rather than geometric height. So what is geopotential here? So it is that work to be done against the gravitational field to raise a mass of 1 kg to that particular point. So which is represented with the symbol phi, and the units are meter square per second square. So how do we express it? So we know that d phi is given by g dz, and also from equation P equal to rho RT we can express the hydrostatic equation. So we can write from this expression we can write g dz is equal to d phi. So this dz we know from this expression I can write it as dP by minus rho. So accordingly I can write, by using this equation for rho, I can write minus RT by P dP, which again I rewrite it again as minus RT differential logarithm of P. I can write minus RT d natural logarithm P. So thus, now if we integrate that expression again, so this is equation 3, we will try to integrate this expression. So we can write instead of d phi, we can write phi of z2 minus z1, which is equal to g naught into z2 minus z1, so which is equal to integral over p2 to p1 t d natural logarithm of p. So now here this z is approximately equal to phi of z by g naught, which is called the geopotential height, where g naught is 9.8 meters per second square. So in terms of z, which we call the hypsometric equation, So we can write Zt as Z2 minus Z1, which is equal to, you bring down this G naught here to the right hand side, R by G naught integral P to P1 temperature times d natural logarithm of P. So this equation we can call it as the hypsometric equation. So where Z, in that expression where we can call Zt as the thickness of the atmospheric layer. So if you trying to calculate Z2 minus Z1, we can obtain the thickness of the atmospheric layer. So between the pressure surfaces P2 and P1. Now let us define a layer mean temperature. So we can write the temperature equation, layer mean temperature like this: integral P2 to P1 differential logarithm of P whole inverse integral P to P1 T differential logarithm of P. So, and a layer mean scale height as H R layer mean temperature by Z naught. This we have written from this equation. So from equation 5 you can write RT by G naught, and you take it as H. H is nothing but layer mean scale height. So from equation 5 I can write it as Z is equal to H. After performing the integration of this right hand side part, you can write Zt is equal to H log P1 by P2. So what do we understand from this? The thickness of a layer, which is Zt, is bounded by isobaric surfaces, is proportional to the mean temperature of the layer. So here mean temperature is represented like this. So the pressure decreases more rapidly with height in a cold layer than a warm layer. That's what we have to understand. So it also follows immediately from equation 6. What is equation 6? We have written this, the layer mean temperature. In an isothermal atmosphere of temperature T, the geopotential height is proportional to the natural logarithm of pressure. So after writing this expression, H logarithm of P1 by P2, the same you can write it as H natural logarithm of P0 by P. So in place of P1 we are taking the pressure at 0 and P is pressure at particular height. So what we have to understand here is thus in an isothermal atmosphere the pressure decreases exponentially with geopotential height by a factor of e power minus 1. So how we can say that? So from this expression I can take out P of Z from here, so that I will get P0 into e power minus Z by H. So that's what here the pressure decreases exponentially with the geopotential height by a factor of e power minus 1. Okay, so this is how you can understand from the hydrostatic equation, which is dP by dZ is equal to minus rho g. So we could able to understand the hypsometric equation, which gives the thickness of the atmospheric layer at two different pressure levels, and from there we can obtain we can understand how pressure decreases exponentially with the geopotential height by a factor of e power minus 1. So this expression is very useful to estimate pressure at a particular height. Thank you.